The next type of application we'll see is the hanging chain, or sometimes you'll see the problem have a hanging rope. So let's just dive right in. Let's take a look at this example. A 50-foot, 150-pound chain hangs vertically from the top of a building. So imagine this 50-foot, 150-pound chain dangling from the roof of a tall building. How much work is done to lift the chain onto the roof? Okay, wow. So imagine standing on top of the roof and you're like almost, you're at the very edge and you're pulling this chain up. So, eventually you'll get the entire chain up onto the roof. And you can imagine as you're doing that at first, you're lifting all 150 pounds of that chain, right? But the more you pull that chain up, the lighter it gets because there's less chain hanging down, after you pull several feet up, let's say. Um, so how much work to pull that whole thing up, right? There's a variable force since the chain is getting lighter as you go. So here's what we'll do. Let me just cover part of this up. I've got a nice drawing here of the building and the chain hanging down. So in the drawing, just be sure that the building is taller than 50 feet. So the idea is that the chain is just hanging loose. It doesn't touch the ground. And here's you at the very top, and you're gonna pull that chain up to the top. So I've got the building, I've got the chain dropping, and this is kind of interesting. So we need an x-axis. So it turns out we don't need an xy plane. We just need an x-axis. So to set it up in a way that's going to make integrating the most natural, say 0 is at the very top, and then extend your x-axis going downwards so that the bottom of the chain is at positive 50 feet. This is going to give us a nice coordinate system to set up our integral. Okay. How are we going to do this? So it turns out the function to describe your chain is very much like Hooke's law. The variable force here will be k times x. F of x equals k times x. However, the k takes on a different meaning here. And the idea is that the more chain you pull up, the lighter it gets. So let me just show you what the units of each of these parts of our equation would be. And that tends to be very helpful for people as they're thinking about their integral and just this variable function, the variable force function. So when we say f of x equals k times x, in this case, right, we're dealing with English units in pounds. So f of x will be pounds because that's the force. So what would that mean for the other units? Well, x is the distance, so that would be in feet. Well, if f of x is pounds and x is feet, then what is k? Well, in order to make this all work, wouldn't k have to be pounds per foot? Right? Because the feet would cancel out and then we'd get pounds over here. All right. Now that's going to be recognizing the units of our constant k, going to be super, super helpful. So think about our chain hanging down. How many pounds per foot is it? You think, well, in our case, it's 150 pounds over 50 feet. It's 3 pounds per foot. So 3 pounds per foot times the number of feet tells us how much force needs to be applied at any given moment. Right at first, we've got 50 feet hanging down. So 3 times 50, we're pulling 150 pounds when it's fully extended. But as it gets shorter and shorter, then x decreases. It's still 3 pounds per foot, but now we're multiplying by a number that is smaller. Very loud truck driving by my house at the moment. Big diesel. They like to drive by and just pause in front of my house when I'm lecturing. That's what it feels like anyway. Okay, so perfect. We've got the function, the variable function is 3 times x, and we can go for our integral. Let me raise this up a little bit. So there we see f of x right there, 3 times x. And we notice that we're going to integrate from 0 to 50. So the work done will be 0 to 50, 3x dx. Now some students like to astutely point out at this moment, this 0 to 50 almost seems backwards. Because doesn't the chain begin at 50 and end at 0? It almost feels like this should be 50 to 0 because it starts at 50 and gets pulled up and it ends, Well, that's true, but when we set up an integral like this, we need the smaller number on bottom and the larger value on top. So we've got to do it 0 to 50. And to maybe help you kind of connect it to, what's actually going on in the problem, it would be the same amount of work if we were to lower a chain from the top to the bottom. If that whole chain was up at the top and we started to lower it slowly down, we would be doing the same amount of work as lifting it up. Now, the human body, and just the anatomy of the body, maybe would find it more difficult to lift that chain up than to lower it. But at the end of the day, you're doing the same amount of work. It's just the anatomy that maybe finds it more difficult. But let's say if there was like a winch, and the winch, not a person, but like a crank, like a pulley. So if the pulley was pulling the chain up versus the pulley letting the chain down, the pulley would experience the same amount of work. It's just, is it heavier at the beginning or is it heavier at the end? It's the same amount of work at the end of the day. Okay, anyway, we can integrate from 0 to 50, almost think of it working backwards, no problem there. And again, we got a very straightforward integral here, right? 3 over 2x squared from 0 to 50. And I'll just tell you the final answer, W, in this case, W equals 3,750 foot-pounds. That's a lot of foot-pounds. That's a heavy chain, 150 pounds? Okay, that was part A of the question. Looks like I've got part B on the next page. Here it is. Let's take it up a notch. Let's attach a 20-pound crate to the end of the chain. So a 20-pound crate is attached to the chain. How much work to lift the chain and the crate onto the roof? Oh my, it wasn't enough just having the chain. Well, what's the use of just lifting a chain up, right? There needs to be something on it. So there's this little crate attached to the bottom of that chain, 20 pounds, and we're going to lift that whole thing. Now, big difference here between the chain and the crate. So as we lift the chain, it gets lighter as we go. But the crate is always 20 pounds. It's 20 pounds the entire trip. It never gets lighter. So that is actually not a variable force anymore. The chain is a variable force, but not the crate. What does that mean for our function or our integral? Well, all we got to do, for f of x, we know that the chain is described by 3 times x, so that's a variable. But the crate is not variable. All we got to do is just add 20 on there. It's like we're just adding 20 pounds. So this is a pounds, and that's just adding another 20 pounds. However long the chain is, there's always that 20 pounds attached to the very end of it. And then we can integrate again from 0 to 50. Work equals integral 0 to 50, 3x plus 20 dx. And again, we can get this pretty fast. 3 over 2x squared plus 20x from 0 to 50. And I'll just tell you the final answer, 4,750 foot-pounds for this one. Now think about that for a moment. Let's compare the two answers. So this answer was 4,750. What was the previous answer? 3,750. So there's exactly a 1,000 foot-pound difference. Where did that come from? Well, the crate, obviously, but because that crate was a constant, weren't we just moving 20 pounds a distance of 50 feet? Well, what's that? Force times distance, 20 pounds times 50 feet? Well, that's 1,000. So there's another 1,000 foot-pounds that just happened. Okay, let's stop this video right here, and we will get to the last application next.